Alright, so this is problem 21 from chapter 6, and the problem says, using the work energy theorem to solve each of these problems, you can use Newton's second law to check your answer, neglect air resistance in all case. Then part 1 says, a branch falling from the top of a 95-meter tall redwood tree starting from rest. How fast is it moving when the branch reaches the ground? And then, so for part A, kind of draw a picture. So, got the ground, got some tree that has a branch that's 95 meters in the air that's falling downwards. And we want to know the velocity of the branch right before it hits the ground. So, we know that force is going to be equal to the mass times the acceleration. We also know that the force times the distance is going to be equal to 1/2 mass times the initial velocity, or the final velocity squared, minus 1/2 the mass times the initial velocity squared. Now, we're not given a force, we're not given an acceleration, we're not given this force or the distance, we're given the initial velocity. We know that that's 0, so this whole term is going to go to 0. So we're going to have to use substitution. So mathematically, I can times both sides times the distance, and that gives me f of s. So I can substitute this for that. This acceleration is going to be the acceleration due to gravity. So we can rewrite the two equations as the mass times gravity times the distance is going to be equal to 1/2 the mass times the final velocity squared. Because of this, we have mass on both sides. That'll cancel out. And then we know the acceleration due to gravity, we know the distance, we're looking for the final velocity, so we just have to solve for that. So we know that the final velocity is going to be equal to the square root of 2 times gravity times the distance, which is then, when we plug in all of our variables, 2 times 9.81 times 95 meters, and that gives us a final velocity that is equal to 43.15 meters per second for part A. Part B of this problem then says, a volcano ejects a boulder directly upwards 525 meters into the air. How fast was the boulder moving just as it left the volcano? So we're going to use these same kind of equations for part B. Force times the distance is going to be equal to the mass times gravity times the distance. But in this case, this is going to be negative. But no, we can just leave it positive. It would depend on your reference frame whether or not gravity was negative. And then we're going to use this same equation. The force times the distance is going to be equal to 1/2 mass, no, this needs to be negative, 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. And we're looking for this initial velocity. And we know that when it reaches the apex of how high up the boulder goes. Its second velocity is going to go to 0. So we'll substitute this term in for this, so we get negative mass times gravity times distance is equal to negative 1/2 mass times the initial velocity squared. Mass cancels because it's on both sides, it's the equal sign, as does the negative, and that's why we had to have the negative here. And so then we're just solving again. So velocity, the initial velocity is going to be equal to the square root of 2 times gravity times the distance, which is then going to be equal to, when we plug all our variables in, it's going to be the square root of 2 times 9.81 times 525, because that's how far the boulder got shot out of the volcano. And then when you do the math, you get that the initial velocity, right as the boulder leaves the volcano, is going to be equal to 101.49 meters per second. And that's your answer for part B. So part A, the final velocity, we solve for the final velocity of a branch falling from a tree. And for part B, we solve for the initial velocity as a boulder is ejected from a volcano.